In this lecture, we'll be talking about vectors in three-dimensional space. So, the coordinate system that we're going to be working with is called the rectangular or Cartesian coordinate system, and it consists of three perpendicular axes, the x, y, and z axes. One thing that's important about this is the orientation of these axes. So, it's ambiguous which direction z points in until we impose this additional condition called the right-hand rule. So you can imagine that if we first started off with x and y in some kind of configuration, just saying that z needs to be perpendicular to two things actually has to x and y. Just it only tells us that z must lie on this line. It doesn't tell us that z needs to be pointed up or down. So we need one additional constraint to fix which direction z should be pointed in. And so the idea is that, well, if we consider the positive directions for x and y, the positive z-axis needs to be pointing in the following way. So imagine that you have your hand stretched out so that your fingers are pointed along whatever axis you would call x. Then next, you curl your fingers so that they end up pointing in the direction of y. Then stretching your thumb out, the direction that your thumb is pointing in, that is the direction that the positive z-axis should be located. So, as another example, if you had that, where do I want to put this? If you had x and y be drawn in the same way that you would normally do two-dimensional pictures, then the positive z, if you place your fingers so that they face x and then curl them so that they face y, you will see that your thumb should be pointed towards yourself. And so you would illustrate this in this way. So that would be where z is located. Okay. A remark I should make is that this way of orienting our coordinate system is the textbook standard way of doing it. I have also seen people I've seen people do. Oh, I guess I'll do it over here. Not that. Sorry. I've seen this being done: x, y, and z. That is also true. That also would work. That also satisfies the right-hand rule. But it's not what this textbook uses, and I don't know if any textbook uses this way. I think most textbooks prefer drawing things in this format, so I will be doing that as well. But one thing in common, notice, is that z is typically facing up. It's usually pointed up, and x and y are flat. Okay. I thought it would be helpful to show how you could sketch a point in three-dimensional space. So this is the way you kind of go about it. Let's sort of talk through this. So suppose that you wanted to sketch the point 1, 2, 3. Well, after you draw the axes for your coordinate system, for your space, what you want to do is make your tick marks so that they are parallel in the right way. So notice that the tick marks for x, they ought to lay parallel to y, and the tick marks for y should be parallel to the x axis. You can imagine that this ends up creating a grid for the xy plane. From that, you then match you draw the point 1, 2, basically. So x should be 1, you extend that, y should be 2, extend that line. That creates this point here, which is effectively, it's the shadow cast by the point 1, 2, 3. It's when you project this point in three-dimensional space down to the xy plane, you end up getting this point here. To finish the drawing, you need to make the height, the z, match up. So you would create the tick marks for the z-axis. And then what's important is to capture the direction of this line. So this line that connects you to the point in question, it's parallel to this line here, connecting the origin to the projected point. So you would normally do this by drawing this line here, and then imagine shifting it up so that the z matches up. And then from that you end up with this point. So this is the point 1, 2, 3. Okay. Some terminology that we have, I guess. Coordinate planes, you can see them in this illustration. So the coordinate planes can be written in this kind of set builder notation, x, y, z, where z coordinate is 0, that's the xy plane. XZ plane has the y coordinate being 0, x and z varying freely. And the YZ plane has the x coordinate being 0, y and z varying. And well, the illustration should help with visualizing how these things look like. Right? The xy plane contains the x and y axis. The xz plane contains the x and z axis. And yz plane contains y and z axis. Right. So octants. The word octant is analogous to the word quadrant in 2 dimensions. So in 2 dimensions, you have your coordinate axes, which separate off the 4 quadrants in your 2-dimensional space. In 3 dimensions, we have these coordinate planes, and they divide the 3-dimensional space into these 8 different pieces, and these pieces are called octants. So in this illustration, you have that these octants are actually given a label. So, for example, this one in the center has all 3 things being positive. These 3 are like the signs of the x, y, and z axes. So in this one, all 3 coordinates are positive. Whereas, say in this one, you have that x is negative, y and z are both positive in this quadrant that is sort of in the back. Okay. The distance formula gets generalized to this in 3 dimensions. So you'll notice that if we ignore this last term, this would just be the distance formula in 2 dimensions. And what I'm illustrating here, or what I'm doing here, is I'm trying to illustrate that you can build up the 3-dimensional distance formula from the 2-dimensional distance formula and just right triangle. So you do end up using the Pythagorean theorem in this. So in this picture, you have P1 and P2. These are the 2 points that you want to find the distance between. And what you do is you kind of incrementally get closer to that goal. So you have this auxiliary point here, this x2, y2, z1. So notice that we've traveled, so this point lies on the xy plane, right? It has the same z height as the point P1. So it lies on the same plane, a plane that's parallel to the xy plane. But the x and y corners are different. So it's like this is the projection of P2 down to the plane that P1 is on. We can calculate the distance between these 2 points by using the 2-dimensional distance formula, which would be this expression. And this length, well, these 2 points only differ by their z-coordinate. So this length is just going to be how far they are separated in the z direction, in the z direction. The absolute value here is just because x and z1 and z2 might be flipped if you were to sketch it accurately. Like it could be that z2 is less than z1, in which case graphically this point should actually be below. To get rid of this issue, we just say that it's the absolute value of the 2 things. Okay. Now the important thing to recognize about this is that in orange, right? In orange, this is a right triangle. This line, which is labeled D1, is perpendicular to this line. And the hypotenuse is the distance that we're after between points P1 and P2. So in order to calculate the length of this hypotenuse, we just use Pythagorean theorem. We do d1 squared plus this this difference squared. Add them, take the square root, which is here. And then, of course, if you square d1, that gets rid of the square root, so you end up with this, which is exactly the three-dimensional distance formula written above. And then below that, I have an example computation. So this is similar to one of your homework problems. You have determine the distance between a given point and the origin. Well, really, it can be just between any 2 points. The origin is a rather nice point to work with because it just makes everything 0. So you would just set x1, y1, z1 to be 0. So these three terms all become 0, and you end up just squaring the components of the other point. So 3 squared plus 2 squared plus 6 squared, you go ahead and compute that, and you'll get 7. Okay. Now for equations in 3-space. So the planes, the coordinate planes, over here, we gave them a set theoretic notation, but you could also describe them just by equations. So the xy plane has the z-coordinate being 0, xz plane has y being 0, and yz plane has x being 0. What you can do with this is then translate the planes by modifying this value, 0. So you can imagine that, I guess I should draw it. So x, y, and z. If we wanted to look at the, well, okay, let's be a bit abstract about this. So z is equal to a. This would be the plane that is parallel to the xy plane at the height a. And so it would be, I guess I'll use black to color it. So it would look something like this, intersecting the z-axis at the point that I have blackened. Okay. Okay. And now this problem is similar to one of yours. So you're given some equation and you're asked to describe the set of points that satisfy the equation and to graph the equation. So in particular, I have this, y minus 5 times z minus 6 equals 0. So the only way that the product of two things can be equal to 0 is if one of the two things is 0. So either you have y minus 5 equals 0 or z minus 6 equals 0. So that ends up creating two equations. Y is equal to 5 or z is equal to 6. And these things are planes. So the way we combine this information is we take the union. The points that satisfy this equation are have either y equals 5 or z equals 6. And well, here's a sketch of this that I did by hand. One thing to be careful, or like to draw these kinds of things, you want to make things look parallel to each other nicely. It's kind of tricky to draw things accurately, but you can see that like this plane in black, I've made it so that the sides are parallel, and this and these two sides are drawn so they're parallel to the x-axis. Same with the plane that is in blue. I'm drawing these two sides to be parallel to the x-axis as well. The other ones are parallel to the y-axis. And their intersection is also parallel. Right? Their intersection forms a line. Right? And to kind of make it look a little bit better, I sort of blacken the point that these planes are supposed to possess. So the plane in blue is supposed to contain the point 0, 0, 6. It's supposed to intersect the z-axis at 6. And the plane in black is supposed to intersect the y-axis at 5. So just emphasize those, and the picture looks fairly decent. Okay. Moving on. Equation of a sphere. Right. So to begin the discussion of spheres, we should start with circles, and bring ourselves down a dimension. So the equation of a circle of radius r centered at the point h comma k is given by the following. Hopefully this is an expression that you'll be familiar with. To generalize this to 3 dimensions, what we do is we tack on an extra term. I'm also changing the way I'm labeling my point to be A, B, C, in which case we end up with this. Okay. The following few things are actually to explain why this equation makes sense. So what you should know is that there's this abstract definition of what a sphere is, which is that it's the collection of points of a fixed distance away from a given center. Right? All the points on a sphere need to be the same distance away from a particular point called the center. And so what we can do is if we have a sphere like this, with the center being ABC and a point on the sphere being XYZ, just abstractly any point on the sphere XYZ. Well, because the points on the sphere must be this fixed distance, which we call r for radius, they have to be this fixed distance apart, we can use the distance formula. Right? So the distance between XYZ and ABC needs to be r. That gives you this. And then by squaring both sides, you wind up with this. That's how we know the equation of a sphere. And you could bring that down a bench and talk about the equation of a circle. That's how we get the equation of a circle as well. Okay. An example we have here, if we are given a particular center and a particular radius, to construct the equation of a sphere, you just insert it into this formula. So this is what you would consider the standard form for the equation of a sphere. So we do x minus a squared plus y minus b squared plus z minus c squared. And maybe just to notice that getting rid of the double negative, it becomes a positive. And radius, of course, should be squared. So all of this is equal to r squared. Okay. Next, vectors in 3 dimensions. So previously we discussed vectors in 2 dimensions, and now we're just upping a dimension. All of the notions are analogous to 2 dimensions. So a vector in 3 dimensions looks like this. We just have an extra component. The 0 vector looks like this. Vector addition and scalar multiplication are an extension of how they worked in 2 dimensions. So we just have this additional thing, and we can still describe it in the same way. So the addition of 2 vectors is the component-wise addition. You just add the components of v and w in this case. And scalar multiplication, you push the scalar into the vector, multiplying each of the components by that scalar, by that number. For magnitude, well, it's distance formula. It's the distance from this, from the associated point to the origin. So it would just be the components squared, summed, and then take the radical. For normalization, it's the same as in the 2-dimensional case. We want to divide by the magnitude of the vector to normalize it, to force the vector to have length 1. I'm using the notation hat to denote that that should be the the unit vector in the direction of v. Right, so you just divide the vector v by its length, and in particular, when we're in three-dimensional case, instead of just having two components, we have this additional third component, which we could pass. We could then pass this scalar in. I didn't bother to type that. That's fine. Standard unit vectors in 3 dimensions. So I and j we had previously, but here, now that we're in 3 dimensions, we need this extra component. So they have this additional z component, which is 0, and we have an additional direction. We have the z direction. So we use the letter k to stand for the unit vector in the z direction, and it has components 0, 0, 1. And just like in 2D, in 3D, we have two different ways to denote or to notate vectors. We can use this kind of angle bracket notation, or we can use this notation that involves the standard unit vectors. Okay. And these last 2 examples just involve working with vector arithmetic in 3 dimensions. So in this problem, we're given the vector PQ should be this, and the initial point is this coordinate. We want to find the coordinate of the terminal point, Q. So the procedure that you should take for this is to think about, well, is to know that the vector PQ is created by doing Q minus P. Right. So I start by letting the coordinate Q, letting Q be the coordinate x, y, z. Right? X, y, and z are what we want to figure out. So the vector PQ from P to Q, which we know is this, it's given to us. Well, the way that we would have computed this in the first place is we would do terminal point minus initial point, Q minus P. So it would be this point minus this point. So and then we do the subtractions component by component. So x minus -2, y minus 3, and z minus 5, which is what I've written here. Now, these 2 vectors need to be equal, which means that their components need to be equal. So 7 should be equal to this expression, -1 this expression, and 3 this expression, which gives us this system of equations, which is pretty easy to solve. You just solve each of them individually. That gives you x is 5, y is 2, z is 8. And so that gives us the coordinates for the terminal point Q. And in this last example, we're asked to normalize the vector A and write it using standard unit vectors. Okay, so the process of normalizing again is you take you determine the length, the magnitude of the vector, and divide by it. So the magnitude of A, we can go ahead and compute it. You square each of the components, sum them, and take the square root. That's this here. And that simplifies to become 3 radical 5. So the unit vector in the direction of A, which I'm denoting by A hat, is A over its magnitude, which means that we can divide by 3 radical 5. Pushing this scalar, 1 over 3 radical 5, into each of the components of the vector A, which then gives us this. And then lastly, I re-express it so that it's using standard unit vectors. And that's all I have for this lecture.